Welcome to this explainer. Today, we're going to completely demystify the precise mechanical logic behind TCP data transfer. Seriously, if you've ever stopped to wonder exactly how your computer ensures that not a single byte of a massive file gets lost over our wildly chaotic internet, well, you're in the exact right place. We're going to break down how data moves, how it's tracked, and how it recovers from errors across complex networks. Let's get right into it.
Here is our roadmap for this session. We'll start with the anatomy of the send and receive buffers, look at the dynamic variables tracking our data, map out the transfer timeline, explore how TCP survives network chaos, and finally, apply all this operational logic to some actual gate exam numericals.
Before we get into the heavy lifting, we absolutely need to lock down our core vocabulary. You are going to hear these two terms constantly. First is the MSS, or maximum segment size. Think of the MSS simply as the biggest possible shipping box you're allowed to use. It dictates the absolute largest payload a single TCP segment can carry. Second is the ISN, the initial sequence number. Because TCP meticulously tracks every single byte, the ISN is just the very first tracking barcode generated for our data stream.
All right, Section 1. Let's explore the TCP staging ground, looking specifically at buffers and pointers. Think of the send buffer like a highly organized warehouse loading dock. Your computer's application writes data into this buffer, and TCP is responsible for actually sending it out the door. To manage this without total chaos, TCP uses incredibly strict tracking variables. Last byte written tracks what the application has just dropped off. Last byte sent tracks what has physically been put on the network wire. And last byte act tracks what the receiver on the other side has successfully confirmed. These sequence numbers update in real time, moving smoothly from left to right as the data gets processed.
Now flip that perspective over to the receiver buffer. This is the receiving dock. It is just as meticulously organized, but obviously with a different set of priorities. Over here, TCP is tracking the last byte read, meaning the data the server application has actually pulled out of the buffer to use. Meanwhile, the next byte expected tracks exactly what piece of data TCP is anticipating from the network next. And here's the catch. If the application doesn't read the data fast enough, that buffer fills up completely.
Moving on to Section 2, let's zoom in on those tracking variables and how they constantly monitor the data.
You can think of these variables as the relentless tracking system of an elite postal service. On the sender side, we constantly monitor what's written, sent, and acknowledged. On the receiver side, we monitor what's received, expected, and read by the application. By working together in total harmony, these two sets of variables guarantee that not a single byte of data is dropped, duplicated, or processed out of order. It's a beautifully synchronized dance.
So here's where the logic gets really interesting. How the receiver dynamically consumes data to free up space. When the receiving application reads a chunk of data, let's call it k bytes, the last byte read pointer mechanically shifts forward by exactly k. So mathematically, the new last byte read equals the old last byte read plus k. This simple arithmetic is what continuously clears space in the buffer from the beginning, allowing fresh network traffic to keep flowing in.
Section 3. Let's watch this physiology in action by looking at the data transfer timeline.
This scenario brilliantly illustrates the TCP handshake logic in motion. When a sender transmits a payload, let's say the very first byte is sequence number 501, and the payload is 100 bytes long. That means it contains bytes 501 through 600. When the receiver successfully gets those bytes, it mathematically replies with an acknowledgement number of 601. It is effectively telling the sender, hey, I securely received everything up to byte 600. The very next byte I expect you to send me is 601.
I really want you to treat this math not as some abstract networking concept, but as a predictable mechanical gear turning. Step 1. Look at your current sequence number. Step 2. Look at how many bytes are in your payload. Step 3. Just add them together. Current sequence number plus payload equals the next sequence number. That sum is exactly what the receiver will fire back as the acknowledgement number.
Watch how this builds when we're sending multiple segments back to back. The first segment starts at 501. The payload is 100 bytes, so the receiver acknowledges 601. The sender immediately fires off the next segment starting at 601. The payload is 100 bytes again, so the receiver acknowledges 701. So 501 becomes 601, which becomes 701. We are creating a perfect, unbroken, mathematically sound chain of tracked packages.
All right, Section 4. What happens when this perfect postal service hits a hurricane? Let's talk about network disruptions.
TCP handles chaos beautifully, but it does so because it adheres to a very strict set of rules. First, it fully expects the packets will be lost in transit. Second, when they are, the receiver will start shouting out duplicate ACKs. Third, the sender relies on strict timeouts to know exactly when to retransmit. And fourth, and you need to remember this, it's the golden rule of TCP. Acknowledgements are always cumulative. They always represent the highest contiguous byte received in perfect order.
Let's picture a failure in action. Imagine a sender transmits 4 segments at once. The first one, starting at 501, arrives perfectly. But then, segment 601 and 701 just get lost in the network. Poof, they disappear. However, that 4th segment, 801, successfully makes it to the receiver. The receiver instantly notices there's a huge gap. It got the 500s, it got the 800s, but the 600s and 700s are just entirely missing.
Because TCP demands strict, unbroken order, the receiver straight up refuses to acknowledge segment 81. It can't. Instead, it stubbornly sends back a duplicate ACK for 601. It's basically saying, listen, I don't care what you just sent me. The last thing I received in perfect sequential order was 600. Send me 601. And it will keep shouting this duplicate ACK over and over until the sender realizes something went terribly wrong.
Eventually, the sender's timer runs out and it realizes it needs to retransmit those missing 601 and 701 segments. Once those missing pieces finally arrive, the cumulative nature of TCP totally shines. Remember, the receiver already had segment 801 waiting patiently in a buffer. So when 601 and 701 finally plug the gap, the receiver combines the acknowledgements. It doesn't ask for 801 anymore. It instantly jumps the ACK number entirely forward to 901, clearing the whole backlog in one massive, brilliantly efficient step.
Finally, Section 5. It is time to put this operational logic to the test with some GATE exam numericals.
If you're aiming for top marks on computer science exams like the GATE, or if you simply want to prove to yourself that you've mastered this concept, let's apply our rules to a classic exam question. We have 3 consecutive TCP segments. Each segment carries exactly 1,000 bytes of user data. We are told the sequence number of the very first segment is 13,000. The question asks, what is the sequence number field value in the header of the 3rd segment?
Now don't just guess here, visualize the timeline. We can track our packages exactly as we did earlier. The first segment starts at sequence number 13,000. Because it carries 1,000 bytes, it encompasses bytes 13,000 up through 13,999. The mechanical gear turns. The second segment must pick up right where the first one left off.
Following our formula, we take the initial sequence number of 13,000 and add the payload of 1,000. That gives us 14,000 for the start of the second segment. Then we take that 14,000, add the payload of 1,000 again, and that gives us the starting sequence number for our target, which is the 3rd segment.
Which means the exact sequence number resting in the header of that 3rd segment is perfectly predictable. It's 15,000. If you follow the mechanical rules of TCP step by step, you literally cannot get this wrong.
You can even reverse engineer this logic. Think about a scenario where an exam tells you that 2 back-to-back segments have sequence numbers of 5,000 and 9,000. You don't even need to be told the payload size. You just subtract. 9,000 minus 5,000 means that first segment absolutely had to carry exactly 4,000 bytes of data to push the sequence number that far forward. It's that straightforward.
So we've seen the staging buffers, the headers, the math, and the recovery protocols, but I want to leave you with a massive final thought to ponder. Today, we just tracked a few hundred bytes, but considering TCP relies on these incredibly strict buffers, exact sequence numbers, and constant back-and-forth acknowledgements, how does this exact same mechanical logic manage to scale up, handling billions of terabytes and millions of simultaneous connections across the globe every single second, without the entire internet just grinding to a halt? Think about the pure elegance required for that kind of scale. Thanks for joining me on this explainer, and I'll catch you next time.